Welcome to Study Smart Academy.
Today in this video, we will learn Class 10th Chemistry, Chapter 2, Metals and Nonmetals.
Exactly. But before we really get into the definitions, I want you to imagine a metal that's so incredibly soft, you could actually slice it in half with a plastic butter knife.
Yeah, like cutting through butter.
Right. But if you were to drop that exact same slice of metal into a regular glass of water, it would violently explode.
Which is crazy to think about.
It is. So today we are diving deep into the bizarre, kind of hidden personalities of the elements all around us.
That's right. Because by the end of this lesson, you're going to understand the actual chemistry behind everyday objects. We're going to explore why the salt on your fries acts the way it does, how we pull pure metals out of the dirt, and even the invisible battles happening right now on the surface of a rusting bicycle.
So let's start with the basics. Physical properties. Like, how do we visually and physically separate a metal from a nonmetal?
Well, normally metals have a very standard resume, right? They are solids at room temperature, they're hard, they're strong.
And they have that metallic shine, which in chemistry we call luster.
Right, luster. They are also highly malleable, meaning you can beat them to very thin sheets. Think of the aluminum foil in your kitchen.
Exactly. And they're ductile, meaning they can be drawn or stretched into thin wires, like the copper wires hidden inside your walls.
Plus, metals typically have very high melting and boiling points. They're dense, heavy for their size, and they're excellent conductors of both heat and electricity.
And the reason they're such good conductors is because they have these free electrons just ready to carry that energy.
Spot on. Finally, they are sonorous, meaning if you strike them, they make a ringing sound, like a school bell.
Right. Now, nonmetals, generally speaking, are pretty much the exact opposite. They're dull, they're brittle, poor conductors, definitely not sonorous, and they can exist as a solid, a liquid, or a gas.
But wait, chemistry is full of rule breakers. So are there exceptions to these physical properties?
There absolutely are, and we like to call these the golden exceptions. Let's tag team these because they are super fascinating.
Okay, let's do it.
So for state of matter, we said metals are solid, but mercury is a metal that is completely liquid at room temperature.
Right, like in old thermometers.
Yeah.
And meanwhile, nonmetals can be literally anything. Carbon is a solid, bromine is a liquid, and oxygen is a gas.
What about hardness? Because we just said metals are tough.
They are, but those metals you mentioned earlier, sodium, which is Na, potassium K, and lithium Li, they are soft enough to cut with a knife.
And on the flip side of that, diamond is a nonmetal, right? Made
Yeah.
entirely of carbon. Yet it is the hardest natural substance on planet Earth.
Exactly. Then there's melting points. Metals are supposed to meet massive, blazing furnaces to melt. But the metals, gallium and cesium, they have such incredibly low melting points that if you just place a solid chunk in the palm of your hand, your body heat alone will melt it into a puddle.
That is so cool.
Hmm.
As for luster, we expect nonmetals to be dull. But iodine is a nonmetal that actually has a beautiful, shiny metallic surface.
Right. And finally, conductivity. Nonmetals are famously bad conductors.
Yeah, usually.
But graphite, which is the nonmetal carbon inside your pencil, is a fantastic electrical conductor. And surprisingly, the metals lead and mercury are actually very poor conductors of electricity for metals.
Whereas silver and copper are the absolute best conductors.
So, okay, now we know what they look and feel like. But what happens when these elements interact with the world around them? Let's move to chemical properties.
Right, starting with the air we breathe. Oxygen. The general rule you need to write down is this. Metal plus oxygen forms a metal oxide.
And a quick note, these metal oxides are basic in nature. If you test them in the lab, they will turn red litmus paper blue.
Right, but the way they react varies wildly. Let's start with the really vigorous reactions. Sodium and potassium are so desperate to react that they will literally catch fire in the open air.
Which is why they must be kept completely submerged in kerosene oil, just to keep them safe from the air.
Exactly. Let's break down the chemical equation for sodium reacting with oxygen. We start with 4 atoms of solid sodium, so that's 4Na, plus oxygen gas, which is O2.
And they react to form 2 molecules of solid sodium oxide. So the product is 2Na2O.
Now, what happens if we dissolve that basic oxide in water? We take that Na2O plus H2O, and we get 2 molecules of sodium hydroxide.
Right, 2NaOH. And potassium behaves almost exactly the same way. Potassium K plus oxygen O2 gives potassium oxide K2O.
And if you dissolve that in water,
K2O plus H2O gives 2 molecules of potassium hydroxide, 2KOH.
awesome. So those are the crazy ones. Now, what about moderate reactions?
Well, these don't explode, but they still put on a show. Magnesium burns with this blindingly bright white flame.
Right. The equation there is 2 magnesium atoms, 2 Mg plus oxygen O2 yields 2 molecules of magnesium oxide, 2 MgO.
And if we dissolve that in water, the NGO plus H2O yields magnesium hydroxide, which is MgOH twice.
Now, aluminium's a really cool one. It reacts with oxygen, but it forms a tough protective shield around itself.
Yeah, the equation is 4Al plus 3O2 yields 2 molecules of aluminium oxide, 2Al2O3.
Then there's iron. Now, a solid block of iron won't catch fire, but iron filings will burn vigorously. 3 Fe plus 2O, 2 yields iron oxide, Fe3O4.
And copper doesn't burn either, but if you heat it, it forms this black coating. 2Cu plus O2 gives 2CuO.
And let's note that silver and gold are completely unfazed. They do not react with oxygen at all, even at really high temperatures.
Which actually brings us to a very special concept, amphoteric oxides. We just said metal oxides are usually basic.
Right.
But amphoteric oxides are like chemical chameleons. They can show both acidic and basic behaviors to form salt and water, totally depending on what they're reacting with at the time.
Let's spell out the reactions for aluminium oxide, Al2O3. First, acting as a base when it meets an acid.
Okay, so Al2O3 reacts with 6 molecules of hydrochloric acid, 6H2O.
And that forms 2 molecules of aluminum chloride, 2AlCl3, plus 3 molecules of water, 3H2O.
But if we introduce it to a strong base instead, it suddenly acts like an acid.
Right, so Al2O3 reacts with 2 molecules of sodium hydroxide, 2NaOH.
And that forms a new salt called sodium aluminate. The formula is 2 molecules of NaAlO2 plus water, H2O.
Zinc oxide, ZnO, is our other amphoteric chameleon. If we pair it with an acid, ZnO plus 2HCl gives zinc chloride, ZnCl2 plus water, H2O.
But with the base, ZnO plus 2 NaOH gives sodium zincate, which is Na2ZnO2 plus water.
So we know oxygen makes these metals corrode or even catch fire. But what happens if we introduce them to something even more common, like water?
The reactivity actually changes based on the water temperature. The general rule here is metal plus water yields a metal hydroxide plus hydrogen gas, H2.
Or, for less reactive metals, the rule is metal plus steam yields a metal oxide. Notice that's an oxide, not a hydroxide plus hydrogen gas.
Let's start with cold water. Sodium and potassium react violently. The equation for sodium is 2Na plus 2H2O liquid, and that yields 2NaOH plus hydrogen gas, H2, plus a massive amount of heat.
Yeah, it's so incredibly exothermic that the escaping hydrogen gas just instantly catches fire.
Potassium is identical. 2K plus 2H2O yields 2KOH plus H2 plus heat.
Now, calcium also reacts with cold water, but it's less violent, so it doesn't catch fire. Instead, something really fascinating happens.
Right. The bubbles of hydrogen gas form, but they stick to the surface of the heavy calcium. They act like little life jackets, causing the metal to actually float.
I love that visual. The equation is calcium Ca plus 2H2O liquid yields calcium hydroxide, CaOH twice, plus H2 gas.
Moving up the temperature scale, magnesium needs hot water to react, and it also floats due to those trapped hydrogen bubbles.
The equation is Mg plus 2H2O liquid yields magnesium hydroxide, MgOH twice, plus H2.
But some metals are stubborn. They require the high energy of steam. Aluminium, zinc, and iron fall in this category.
And crucially, like we said earlier, they do not form hydroxides. They stop at forming metal oxides.
Let's look at those steam equations carefully. For aluminium, 2Al plus 3H2O gas yields aluminium oxide Al2O3 plus 3H2.
For zinc, Zn plus H2O gas yields zinc oxide, ZnO plus H2.
And for iron, 3Fe plus 4H2O gas yields iron oxide, Fe3O4 plus 4H2.
And, really importantly, lead, copper, silver, and gold have absolutely NO reaction with water. Not hot, not cold, not steam, nothing.
So let's push them harder. What happens when we drop metals into dilute acids? The rule is metal plus dilute acid yields a metal salt plus hydrogen gas.
Okay, imagine a row of test tubes, right?
Yeah.
Filled with dilute hydrochloric acid, HTL. We drop magnesium into the first one. It produces vigorous, rapid hydrogen bubbles.
The equation is Mg plus 2HCl yields magnesium chloride, MgCl2 plus H2.
And if we use sulfuric acid instead, it would be Mg plus H2SeL4 yielding magnesium sulfate, MgSO4 plus H2.
Now, in the next tube, aluminium produces moderate bubbles. 2Al plus 6HCl yields 2AlCl3 plus 3H2.
Next tube, zinc produces very slow bubbles. Zn plus 2HCl yields ZnCl2 plus H2.
And iron produces incredibly slow bubbles. Fe plus 2 HCl yields FeCl2 plus H2.
So just by watching how fast the bubbles form, we can see the decreasing reactivity order. Magnesium is greater than aluminium, which is greater than zinc, which is greater than iron.
And copper, silver, and gold, they sit all the way at the bottom. They do not react with dilute HCl or H2SO4 at all.
But here's a question for you. Is hydrogen gas always evolved when a metal meets an acid?
Well, actually, no. And this brings us to what we call the nitric acid exception. Nitric acid, HNO3, is kind of a chemical bully. It's a very strong oxidizing agent.
Right, so when a metal reacts with it, hydrogen gas is initially formed, but the nitric acid immediately oxidizes that H2 into water, H2O.
While reducing itself into nitrogen oxides like NO2, N2O, or just NO, let's look at copper reacting with nitric acid.
Okay, 3Cu plus 8HNO, 3 yields 3 molecules of copper nitrate. So that's 3CuNO, 3 twice plus 4 molecules of water, 4H2O plus 2 molecules of nitrogen dioxide gas, 2NO2.
See, no pure hydrogen gas is released there at all.
But chemistry loves an exception to the exception. Magnesium and manganese are the only two metals that will evolve hydrogen gas, but only if they are with very dilute nitric acid.
Right. Mg plus 2HNO3 gives magnesium nitrate, MgNO3 twice plus H2 gas.
And manganese MnO does the exact same thing to form MnNO3 twice plus H2.
Before we completely leave acids, we have to talk about aqua regia. It literally translates to royal water in Latin.
It's an intense mixture. If you mix 3 parts concentrated hydrochloric acid with 1 part concentrated nitric acid, you get this fuming, highly corrosive liquid.
It is so powerful it can dissolve absolutely all metals,
Yep.
even indestructible gold.
Incredible stuff. So we see metals react with oxygen, water, and acids. What happens when they face off against each other?
Oh, displacement reactions. The rule here is really simple. A stronger, more reactive metal will kick out a weaker, less reactive metal from its salt solution.
We can see this perfectly in visual experiments. Imagine a beaker of blue copper sulfate solution, CuSO4.
If we drop in a piece of silvery zinc, ZON, the zinc literally displaces the copper. The beautiful blue solution fades to a completely colorless zinc sulfate, and pure copper just falls to the bottom.
The equation is Zn plus CuSO4 yields ZuAnSO4 plus Cu.
Now, if we use an iron nail instead, iron, Fe, displaces copper. The blue solution turns light green as iron sulfate, FeSO4, is formed.
And the nail actually gets coated in a red-brown layer of pure copper. Fe plus CuSO4 yields FeSO4 plus Cu.
Magnesium does the exact same thing. Mg plus CuSO4 yields MgSO4 plus Cu.
But what if copper wants to be the bully? Copper can't displace zinc or iron, they're too strong. But it can displace silver.
Right. If you put a copper wire into a colorless silver nitrate solution, AgNO3, the solution turns blue as copper nitrate forms, and literal silver crystals grow on the wire.
Cu plus 2, AgNO3 yields CuNO3 twice plus 2Ag.
By watching all these fights, chemists built the reactivity series. Let's summarize it. At the top, the most reactive: potassium, K, sodium, Na, calcium, Ca, magnesium, Mg, and aluminum, Al.
Then in the middle, medium reactivity: zinc, Zn, iron, Fe, and lead, Pb.
Then we use hydrogen H as a baseline reference point.
And below hydrogen are the weak, least reactive metals: copper, Cu, mercury, Hg, silver, Ag, and gold, Au.
So now we know how they react, but we really need to understand why. Why are these elements so eager to explode, dissolve, or displace each other?
It all comes down to electrons and a desire for stability. Every atom wants an inert gas electron arrangement. They want what we call a stable octet, 8 electrons in their outermost shell.
And to get there, they have to form bonds. First up, ionic bonds, which are also known as electrovalent bonds. Think of an ionic bond like a billionaire giving away a car to someone who desperately needs one. It's a complete transfer.
I love that analogy. Metals have extra electrons they want to lose. When they lose them, they become positively charged electropositifications.
And nonmetals desperately need electrons, so they take them, becoming negatively charged electronegative anions. Since one is positive and one is negative, they are pulled together by a massive electrostatic attraction.
Let's build sodium chloride, NaCl, step by step. Sodium's atomic number is 11, right? So its electron shells are 2, 8, and 1. It desperately wants to get rid of that one extra outer electron.
And chlorine is 17. Its shells are 2, 8, and 7. It is exactly 1 electron short of an octet.
So sodium donates its 1 electron to chlorine. Sodium becomes an Na plus ion, chlorine becomes a Cl minus ion, and boom, NaCl is formed.
Now look at magnesium chloride, MgCl2. Magnesium's configuration is 2, 8, 2, so it needs to donate 2 electrons.
But a single chlorine atom only needs one. So what's the solution?
Magnesium gives its electrons away to TWO different chlorine atoms. We get 1 Mg2 plus ion and 2 Cl minus ions, perfectly balanced to form MgCl2.
Calcium chloride, CaCl2, works exactly the same way. Calcium donates its 2 outer electrons to 2 chlorines. We also see this in ionic metal oxides.
Like for magnesium oxide, MgO, magnesium transfers its 2 outer electrons directly to a single oxygen atom because oxygen needs exactly 2 to finish its shell. We get Mg2 plus and O2 minus.
In calcium oxide, CaO is exactly the same transfer.
But what happens when a nonmetal reacts with another nonmetal? They both need electrons, right? Neither wants to give theirs away.
Exactly. Since they can't form ions with each other, they are forced to share their electrons. This sharing creates covalent bonds, which form molecules. Think of it like 2 roommates sharing a television.
Let's detail those shared pairs. In hydrogen gas, H2, and chlorine gas, Cl2, the 2 atoms share exactly 1 pair of electrons between them, creating a single bond.
In water, H2O, 1 oxygen atom shares 1 electron with 1 hydrogen and 1 electron with a second hydrogen.
Hydrogen sulfide, H2S, is the same. Sulfur shares with 2 hydrogens.
In chloromethane, CH3Cl, carbon has 4 outer electrons. It shares 3 of those with 3 different hydrogen atoms and shares its 4th with a chlorine atom.
For fluorine gas, F2, the 2 atoms share 1 pair.
And sulfur is amazing. S8 is a molecule where 8 individual sulfur atoms join together in a special crown ring shape. They hold hands in a circle, sharing electrons so every single atom completes its octet.
Because they are built so differently, their properties are totally different. Let's compare ionic versus covalent.
Okay, for particles, ionic compounds are made of rigid grids of positive and negative ions. Covalent compounds are just separate molecules.
For state, ionic compounds are hard, crystalline solids. Covalent compounds are usually liquids or gases.
Because of those strong electrostatic attractions we mentioned, ionic compounds have very high H melting and boiling points. Covalent compounds have weak forces between their molecules, so their melting and boiling points are quite low.
For solubility, ionic compounds dissolve easily in water, but not in organic solvents like petrol. Covalent compounds are the exact opposite. Insoluble in water, but soluble in organic solvents.
But the ultimate distinguishing test is electrical conductivity. Imagine a beaker with 2 wires and a light bulb. If you put solid salt and an ionic compound in the beaker, the bulb stays dark.
Right, because the ions are locked tightly in a rigid crystal and cannot move.
BUT. If you dissolve that salt in water or melt it with extreme heat, the rigid crystal structure breaks down.
Suddenly, those charged ions are free to swim around, carrying the electric current from one wire to the other, and the bulb lights up.
Well, covalent compounds don't have ions at all, so they simply never conduct electricity.
Okay, so now that we understand these elements perfectly, where do we actually get them? That brings us to metallurgy, the extraction of metals.
Since metals are so reactive, you don't just find chunks of pure iron lying on the ground. We find minerals, which are naturally occurring elements or compounds in the Earth's crust.
And if a mineral contains a high enough percentage of a metal that we can extract it profitably, we call it an ore.
Remember this golden rule. All ores are minerals, but not all minerals are ores.
And the dirt, sand, and rocky impurities mixed in with the ore. We call that gangue.
How we extract the pure metal depends entirely on its position in the reactivity series. Let's start at the bottom with low reactivity metals, like mercury and copper.
We extract these by simply heating their ores in the presence of oxygen, a process called roasting. Let's look at mercury. We use its ore, cinnabar, which is mercury sulfide, HGS.
We roast it. 2HES plus 3O2 plus heat yields 2 molecules of mercury oxide, 2HGO plus 2SO2 gas.
Then we just heat that oxide even more. 2HGO plus heat breaks apart into 2Hg liquid pure mercury and oxygen gas.
Copper from copper sulfide, CuS, is similar. Roast it. 2CuS plus 3O2 plus heat yields copper oxide 2Cu2O plus 2SO2.
Then the newly formed oxide reacts with the remaining sulfide. 2Cu2O plus Cu2S plus heat yields 6 atoms of pure molten copper, 6Cu plus SO2 gas.
Now for medium reactivity metals in the middle of our series, zinc, iron, and lead. It is chemically much easier to extract a metal from an oxide rather than a sulfide or carbonate.
So our first step is to turn the ore into an oxide, and we have two different paths for this. Path A is for sulfide ores, and we use roasting heating strongly with excess oxygen.
Right, so for zinc blende ore, 2ZnS plus 3O2 plus heat yield 2VNO zinc oxide plus 2SO2.
Path B is for carbonate ores, and we use a process called calcination heating strongly in the absence of oxygen.
For calamine ore, ZnCO3 plus heat breaks down into ZNO, zinc oxide plus carbon dioxide, CO2.
So whether we use path A or path B, we now have zinc oxide. The final step is reduction. We mix the oxide with coke, which is just carbon, and heat it.
ZNO plus carbon, C, yields pure zinc metal, Zn, plus carbon monoxide, CO. The carbon just steals the oxygen away.
That works great. But what if the metal we want is so reactive that it holds onto its oxygen tighter than carbon can pull? Carbon just isn't strong enough.
That is where thermit reactions come in to save the day. Instead of carbon, we use highly reactive metals like sodium, calcium, or aluminium as reducing agents.
And these reactions are so incredibly exothermic that the pure metal is produced as a molten, white-hot liquid. Let's look at the equations.
For manganese, 3MnO 2 plus 4Al yields 3 atoms of pure manganese, 3Mn plus 2Al2O3 plus massive heat.
My favorite is the railway weld equation. If a train track cracks, engineers put iron oxide and aluminium powder over the crack and ignite it.
Right. Fe2O3 plus 2A yields Al2O3 plus 2 pure atoms of iron, 2Fe plus immense heat. That heat melts the pure iron, flowing directly into the crack and welding the track perfectly.
Finally, what about the high reactivity metals at the absolute top? Potassium, sodium, calcium, magnesium, aluminium.
They have a massive affinity for oxygen. Carbon can't help. Thermit can't help. Instead, we use electricity in a process called electrolytic reduction.
Let's take molten sodium chloride, NaCl. We melt it down and run an electric current through it. At the cathode, which is the negative electrode, the positive sodium ions rush over.
They gain an electron and turn into pure sodium metal. Na plus an electron, E minus, yields Na.
And at the anode, the positive electrode, the negative chloride ions rush over, lose their extra electrons, and pair up to become chlorine gas. 2Cl minus yields Cl2 gas plus 2 electrons.
Now, once we've extracted these metals, they aren't perfect yet. They have impurities. Removing them is called refining, and the most common method is electrolytic refining.
Let's visualize the setup for copper. Your anode, the positive side, is a big chunky block of the impure extracted copper. Your cathode, the negative side, is a razor-thin sheet of perfect, pure copper.
The liquid electrolyte they sit in is an acidified salt solution of copper, specifically copper sulfate, CuSO4, with some dilute H2SO4.
When you turn on the current, atoms from the impure anode dissolve into the liquid. Solid Cu turns into Cu2 plus ions, leaving 2 electrons behind.
At the exact same time, an equivalent amount of pure Cu2 plus ions in the liquid are drawn to the pure cathode, gaining 2 electrons to deposit as solid, perfectly pure copper.
But where do the impurities go? The soluble ones just dissolved harmlessly. But the heavy, insoluble impurities, which are often precious metals like gold and silver, they literally fall to the very bottom of the tank, right below the anode.
And this valuable pile of sludge is famously called anode mud. So now that we have perfectly pure metals, we have to protect them from corrosion, which is the eating up of metals by air, moisture, or chemicals.
The most famous example is the rusting of iron, forming that red-brown flaky substance. The chemical formula for rust is hydrated iron 3 oxide, Fe2O3.XH2O.
And to prove exactly why iron rusts, we have a classic 3-test tube experiment. Tube 1 has an iron nail sitting in half water, half damp air. Observation, it rusts.
Tube 2 has an iron nail fully submerged in boiled distilled water, which removes all dissolved air, and it's sealed with a layer of oil on top. So there is water, but absolutely no air. Observation, no rust.
Tube 3 has an iron nail in completely dry air, and we add a chemical called anhydrous calcium chloride to absorb any trace of moisture. So there is air, but absolutely no water. Observation, no rust.
This perfectly proves that both air, meaning oxygen, and water, meaning moisture, must be present together for rusting to happen.
To prevent this, we block the air and water using physical barriers like painting, greasing, or oiling. But industrially, we use galvanization, which means coating the iron with a thin layer of zinc.
And here is the brilliant mechanism behind it. Zinc is slightly more reactive than iron. Even if the zinc coating gets scratched and the iron is exposed, the iron still won't rust.
Right, because the oxygen will actively choose to attack the more reactive zinc instead. The zinc literally sacrifices itself to protect the iron. We also use tin plating or chromium plating for protection.
Speaking of tin, here's a quick question for you. Why are the metal cans holding your soup coated with tin on the inside and not zinc?
Ah, it's because zinc is more reactive than tin. If we lined food cans with zinc, the natural acids in the food would react with it, creating compounds that would completely spoil the food. Tin is less reactive, keeping your food safe.
Exactly. Other metals corrode too, but sometimes it's helpful. Aluminium reacts with oxygen to form a dull layer of aluminium oxide. But this layer is so tough it acts like a force field, preventing any further corrosion.
We even thicken this layer artificially in a process called anodizing, making the aluminium super durable and easy to dye with colors.
Copper reacts slowly with CO2 and moisture in the air to form a green coating of basic copper carbonate, which is CuCO3.CuOH twice. You can actually clean this green tarnish off using lemon or tamarind juice because the natural acids dissolve the basic carbonate.
Silver tarnishes and turns black because it reacts with hydrogen sulfide gas, H2S, in the air, forming black silver sulfide, Ag2S.
But gold and platinum, resting safely at the bottom of our reactivity series, are highly resistant and won't tarnish for years unless you drop them in that aqua regia we talked about.
Our final topic today is alloys. An alloy is a homogeneous mixture of two or more metals, or a metal mixed with a tiny amount of a nonmetal.
Why do we mix them? Because pure metals have flaws. By alloying them, we can make them stronger, harder, more resistant to corrosion, or even lower their melting points.
Let's detail the most important recipes. Pure iron is too soft, but if we add 0.1 to 1.5% carbon, we create steel, which is incredibly hard and strong.
If we mix iron with chromium and nickel, we get stainless steel, which is tough and absolutely will not rust.
Brass is a mixture of 80% copper and 20% zinc. It is highly malleable and stronger than pure copper.
Bronze is 90% copper and 10% tin. It is famous for being highly resistant to corrosion, which is why ancient statues survive today.
Solder is a 50-50 mix of lead and tin. Pure lead and pure tin have higher melting points, but together their melting point drops drastically.
Right, making solder perfect for melting and welding electrical wires together. Amalgam is an alloy of mercury mixed with any other metal, often used by dentists for fillings.
And duralumin is a brilliant mix of aluminium, copper, magnesium, and manganese. It is incredibly light because of the aluminium, but vastly stronger, making it the perfect material for building aircraft bodies.
Even pure gold needs help. Pure 24-karat gold is far too soft to wear. Jewelers alloy it with small amounts of silver or copper to create 22-karat gold, meaning 22 parts gold and 2 parts alloy, giving it the structural strength needed to actually hold its shape as jewelry.
To wrap up, I want to share a true historical marvel. In Delhi, there is an iron pillar built around 400 BC out of wrought iron. It has stood exposed to the weather for over 2,000 years, yet it hasn't rusted.
How is that possible?
Ancient metallurgists created a thin protective film of magnetic oxide, Fe3O4, on the surface, utilizing the exact principles of corrosion prevention we just discussed today.
That is a brilliant final thought. We just learned how ancient metallurgists protected the iron pillar over 2 millennia ago using basic chemistry. Today, scientists are taking these exact same principles, understanding reactivity, bonds, and alloying to design smart metals that can remember their original shape, or self-heal when damaged in the vacuum of space.
The periodic table isn't just a list to memorize. It's an interactive toolbox for building the future. Think about what kind of revolutionary alloy you would invent if you could mix any of these elements.
Don't forget to like and share this video for more updates. Subscribe to this channel.